All right, so I'm going to start with the FRQ portion. This is one that you actually can do at home because these are questions that I made up. So if we don't get to them in class, you can go ahead and do these at home. All right, so let's look at what this first question is asking. It says the KSP of a salt is 5.3 times 10 to the minus 10. What is the solubility, molar solubility, of silver sulfate in a 0.05 molar solution of silver sulfate? Okay, so KSP, remember, for a salt, all it is products. So if our equation, let me write the equation up here. The equation is going to be Ag to SO4 going to 2Ag plus SO4 2 minus. Now, this is a solid. So this does not appear in the equilibrium expression. And I would say probably 40% of you put a denominator in this problem. There is no denominator. This is a salt with KSP, remember, because that's a solid, and these are aqueous. It's just going to be Ag plus squared, because there's a 2 there, times SO4 2 minus. So this is really extra information, isn't it? I don't really need it. It's just telling me that I have a saturated solution. I have a lot of this. This is really small. I'm saturated. Okay. So now it says, what is the molar solubility? So let's rewrite. I'm going to rewrite this. And I'm going to do a rice table. You don't have to do a rice table for these. We did not do rice tables in the PhET. That's what this is. This is the PhET, right? All right. So what we're going to do is this is R. Now, when I get to my initial, who cares about that? That's a solid. I'm not interested in it. It's not in my equilibrium expression, so I don't care. These are 0. That's how I start. I have this salt. I've got it sitting above my beaker there, and then that's initial, and then I'm going to dump everything in there and then see it reach equilibrium. So my change is going to be in this direction. Who cares about that? This is plus, this is plus, this is 2x, and this is x. That means that the equilibrium concentration of silver is 2x, and the equilibrium concentration of SO4 2 minus is x. All right? So what I'm going to do is x is the molar solubility. That's what we're solving for. The molar solubility is defined as the moles of salt only dissolved in solution. Not the concentration of these, the moles of salt. So I'm going to solve for x. So my KSP is 5.3 times 10 to the minus 10 is equal to what? 2x squared times x. That means that 5.3 times 10 to the minus 10 is equal to 4x cubed. X is equal to 5.1 times 10 to the minus 4 molar. That is, remember, x is change, x is molar solubility. Okay, so now I'm moving on to this problem because I want you to see the difference between x and what's happening here. It says, here's my salt. I have a KSP of 1.4 times 10 to the minus 8. What are the concentrations of each in a saturated solution? That means I'm at equilibrium. That's what that means. It's saturated. Okay? So again, what I've got is I've got PbI2 in equilibrium with its salt and the ions. All right? This is a solid. These are aqueous here. All right. Now, I'm going to do a rice table again because basically what I want is I need to find x in order to find the equilibrium concentrations. Equilibrium concentration is always one more step past x. All right? So here's R. Here's I. Don't care about that. 0, 0. Change. Who cares about that? Again, this is going to be plus and plus. This is going to be x. This is going to be 2x. Draw my line. My equilibrium concentrations are x and 2x. Okay, that's what my concentrations are. In fact, I'm going to put little things here. My equilibrium concentration of lead is X, and my equilibrium concentration of I is 2X. So what I've got to do, though, is I've got to find X first, don't I? So what I'm going to do is I'm going to use KSP to do that. So I know that X times 2X squared is 1.4 times 10 to the minus 8. 4X cubed is 1.4 times 10 to the minus 8, and X is equal to 0.0015 molar. So I've got to plug it in here. These are my equilibrium concentrations of my ions. That means that lead is automatically 0.0015 molar, and I is 2 times that, or 0.0030 molar. All right, so this next problem is going to be a slightly different twist. Now they want to know what KSP is. They're asking for KSP, and what are they giving us? They're giving us X. This is the solubility of this. This is X. So if I want to find KSP, I can solve for KSP in terms of X and substitute. Super easy. So let's do that. All right. So what I've got is, I made this up actually, VB E3 is in equilibrium with VB 3 plus 3E minus. My context clues are right there. That should tell me exactly what my charges are. All right. Again, now, what are my initial concentrations? Nothing here. Now, I don't have anything here, but what did I do? I added this salt. That's a NAP. So I have 0.20 molar of this in solution. My change is going to be, I don't think I'm even going to put a 0 there. I'm just going to put nothing. My change here is going to be plus and plus. This is X and this is 3X. So when I go to solve E, I get X and 0.20 plus 3X. Now remember that this is really small compared to this. What that means is whatever small amount of E minus I have in solution from this process is negligible because it's just overwhelmed by that number. So I don't really have to worry about that. So I'm going to go up here and continue. So I've got to solve for KSP. So what I'm going to do is I'm going to say X, right, because my KSP is going to be X times 0.2 cubed, because it's this times this cubed. But again, I don't need that. Now, what's X? Well, it told me that X is this. And this is where people went wrong. They thought this was KSP. No, no, no. If it says it's a solubility, that's X. I put that right in there. And I get 2.5 times 10 to the minus 10 times 0.2 cubed is 2.0 times 10 to the minus 12, and that is the answer for that. Now this problem is slightly different still. We're going to ask, will a precipitate occur? This is a Q problem, right? If we shift towards products, that's ions. If we shift towards reactants, that's salt. So we're going to see what Q will tell us about which way we're shifting. So in this case, we've got VB F2 in equilibrium with VB 2 plus 2F minus. So QSP, if you want to look at it that way, is going to be the concentration of VB2 plus times the concentration of F plus squared. Let's plug and chug. Here they are. That's how I'm delivering them, right? Large quantities. So I've got 4.00 times 10 to the minus 4. Remember, molar times 0.0700 squared is 1.96 times 10 to the minus 6. That is greater than 9.5 times 10 to the minus 8. So Q is greater than K. We can use our number line if we want. Q is here, K is here. Shift left. When I shift left, remember, salt is on this side, ions are on this side. Shifting this way gives me a precipitate. So yes, a precipitate forms. All right, the next few, I'm just going to give you the answer, and you can kind of come into tutorials or enrichment if you'd like and work through these. This one should be Q is less than KSP. Therefore, I'm going to have a precipitate, no precipitate forms. Because remember that if Q is less than K, it's going to shift to products. That means more products is more ions. Ions are on this side, salt is over here. This is shifting towards ions, so it's dissolving. This way, we're shifting towards salt with the precipitate. So we're shifting in this direction, therefore no precipitate forms. In this case, this is just another K equation. You're going to set up a rice table, and when you get your equilibrium concentrations, it's just like the problem we worked in the multiple choice section. This is exactly the same thing. You're going to set all that equal to 3.5, and the number you actually get is 0.25 atmospheres hydrogen. In this one, this is just a plug and chug. I've got 1 mole, 0.291 moles, and 0.75 moles. I plug all that in. That's going to be 0.75 or 0.75. Let me just write this out. 0.75 times 0.291 divided by 1 squared is equal to 0.218, which is greater than K. Therefore, I shift left.